In this video, we are going to look at factors that affect rates of SN2 reactions. Factors that affect reaction rate in decreasing order of importance are steric hindrance in the substrate, electronic effects, nature of the nucleophile, nature of the leaving group, and the solvent. So we'll examine them now in this order. By far, the most important factor is steric hindrance in the substrate. SN2 reactions are highly sensitive to steric hindrance, and hindered substrates either don't undergo SN2 reactions or undergo at very slow rate. And of course, then we can draw a conclusion that methyl compounds will react the fastest. Primary will still react at rather fast rate, but a bit slower than methyl, then secondary, while tertiary don't undergo SN2 reactions. So tertiary compounds are too hindered to undergo SN2 reactions. And now we can examine reasons behind the effect of steric hindrance. When we consider methyl substrate, we can see from the formula on the top that there is no steric hindrance. There are 3 hydrogens to the back from the side where nucleophile is attacking, and 3 hydrogen atoms don't provide any hindrance to the attacking nucleophile. You can see in the middle ball and stick model, and most importantly at the bottom space filling model. Space filling model shows steric hindrance very well. And here approach of the nucleophile is shown by green arrow, and you can see that there is nothing to impede or to get in the way of the nucleophile as it is interacting with the backside of the carbon atom. Backside of the carbon atom is clearly exposed and is open to the attack by the nucleophile. Now we can see completely opposite effect. We can see tertiary substrate. So we can see on the top formula, perspective drawing with 3 methyl groups, so tertiary butyl bromide, and we can see that backside of the carbon-bromine bond is basically hidden in a cage, almost in a cage of the substituents, and that hydrogens of the 3 methyl groups completely prevent attack of the nucleophile. So in the middle there is ball and stick model, and particularly at the bottom space filling model clearly shows that approach of the nucleophile is not possible without it first bumping into hydrogen atoms and of course bouncing off them. It simply cannot go through them. And you can see from the space filling model that actually backside of the carbon atom attached to bromine is not visible. It's hidden by methyl groups. So that shows effect of steric hindrance, how steric hindrance prevents approach of the nucleophile and prevents SN2 reaction from occurring. And finally here we have another example. That's an example of primary substrate but with neighboring large group. Neighboring group is isopropyl group. So that one will slow down attack of the nucleophile. So reaction won't be impossible, but it will occur at a slow rate. And you can see from the ball and stick model in the middle and space filling model that nucleophile will have to approach a little bit under an angle, so orbital overlap will not be the best, and nucleophile will have to basically squeeze between the atoms to interact with backside of the carbon-bromine bond. Next effect that has considerable importance in SN2 reactions is electronic effect. And that effect operates when there is neighboring pi bond. So when there is pi bond next to the reactive center, next to the sp3 carbon that carries the leaving group. So pi bond means that next to the sp3 carbon there is either double or triple bonds. So there is a substituent that contains double or triple bonds. And that substituent, as you can see in the last example on the far right, could be heteroatom, could involve heteroatoms like carbon-oxygen double bond. The reason behind electronic effect, and these electronic effects considerably increase reaction rate. So all these compounds react in SN2 reactions readily at very fast rate. So reactions of these compounds are very fast. So these compounds react really fast with nucleophiles and give cleanly products that result from SN2 reaction. The effect is twofold. One is that neighboring unsaturated group provides very little steric hindrance, because if this is double bond, then those are sp2 hybridized carbon atoms. They are planar, they are flat, and as planar or flat, they provide very little steric hindrance. Basically, they always can get out of the way. That plane can always get out of the way of the approach of the nucleophile and not impede the attack of the nucleophile. And with triple bond, it's even better because triple bond is linear, it's like a rod, and effectively offers no hindrance to the approach of the nucleophile. So compared to the tetrahedral carbon, simply sp2 or sp3, sp2 or sp carbon offer no steric hindrance. Another effect is even more important. Due to electron delocalization of the neighboring pi electrons, transition state is stabilized. In the transition state, remember from the previous video that carbon atom is sp2 hybridized. Being sp2 hybridized means that it has a p orbital, atomic p orbital in it. And that p orbital can accept those neighboring pi electrons. So neighboring pi electrons delocalize into the developing atomic p orbital and stabilize transition state. As they stabilize transition state, energy of the transition state is considerably lower, which means that the activation energy is lower, and of course, as a consequence, reaction rate is faster. Since this is nucleophilic substitution reaction, nature of the nucleophile affects the reaction rate, with strong nucleophiles reacting at a fast rate, while weak nucleophiles either reacting at slow reaction rates or not reacting at all. So obviously, you have to be able to recognize strong nucleophiles and to arrange nucleophiles in the order of increasing or decreasing strength so that you can determine which one reacts faster than the other. So strength of the nucleophile depends on the charge. If same atom is the atom that is bearing free electron pair, that is electron pair donor, then negatively charged atom is stronger nucleophile compared to neutral atom. So for example, hydroxide anion is much stronger nucleophile compared to water. And same goes for amide anion. It's much stronger nucleophile compared to ammonia. Consider also electronegativity. Less electronegative atom when comparing nucleophiles in the same row of periodic table, less electronegative atom is stronger nucleophile compared to more electronegative. Less electronegative atom is better electron pair donor because it doesn't have as much tendency to attract that electron pair. So hydroxide anion is much stronger nucleophile than fluoride. Also iodide anion is stronger than fluoride, again lower electronegativity, and ammonia stronger than water. In each of these cases, it's the electronegativity effect. And finally, steric hindrance plays very important effect on strength of nucleophiles. Nucleophiles that are not hindered are generally much stronger because there is nothing to impede its ability to donate free electron pair. Nucleophiles that are hindered are either poor nucleophiles or are not nucleophiles at all. So, for example, hydroxide and methoxide anions are both strong bases and strong nucleophiles. Hydroxide a bit stronger because it's less hindered. On the other hand, tertiary butoxide is a very strong base, but it's not a nucleophile at all. We classify it as weak nucleophile, but for practical purposes, it's not nucleophile at all. So something like tertiary butoxide or isopropoxide, anion of isopropyl alcohol, are either weak nucleophiles or very poor nucleophiles, and they don't generally undergo SN2 reactions very well. Tertiary butoxide is best known example, and we use tertiary butoxide as an ion when we actually want to avoid substitution reaction because it's such a poor nucleophile that doesn't undergo substitution reactions. 3 methyl groups in this case provide steric hindrance and prevent oxygen from effectively donating its free electron pair. Here is the order of strength of nucleophiles, but that depends also on the solvent. This particular order has been determined in methanol. And you will notice that large atoms, the atoms that are both large and have low electronegativity and, of course, negative charge are strong nucleophiles, while smaller atoms without the charge are weaker nucleophiles. All of these are reasonably good nucleophiles in substitution reactions. But Those at the left are much stronger, at the right much weaker. The leaving group, of course, affects reaction rate. Good leaving group leaves easily and reacts at fast rate, poor leaving group at slow rate. So carbon forms the weakest bond to iodine atom. And since this is the weakest bond, then iodine is the best leaving group. And its relative rate compared to fluorine, if you look at the bottom, carbon-fluorine bond is very strong, and fluorine is actually effectively not a leaving group. So if we set that as a standard, if we set reaction rate of alkyl fluoride with hydroxide as 1, then alkyl chlorides react 200 times faster. So that's a better leaving group because carbon-chlorine bond is weaker compared to carbon-fluorine. And then carbon-bromine bond is much weaker, and that's already a good leaving group, 10,000 times faster rate. And then carbon-iodine, which I already mentioned, the best leaving group, the weakest bond, 30,000 times faster reaction rate. We can estimate leaving group ability even without knowing strength of carbon leaving group bond. And we can estimate that from a base strength. Weak base in general is a good leaving group, strong base is a poor leaving group. So when we arrange halogens, halide anions in the order of base strength, iodide anion is the strongest, is the weakest base and the best leaving group, while fluoride anion is the strongest base and the weakest leaving group. You can also memorize that by knowing that hydroxide anion is strong base. It's actually very poor leaving group. On the other hand, water is weak base and excellent leaving group. So weak base, excellent leaving group, strong base, poor leaving group. Strong base because it's unstable, and unstable base will tend to reform a bond with the electrophile, and so that's why it doesn't want to leave. Solvent also has effect on rate of SN2 reactions. Of course, SN2 reactions have to be carried out in polar solvents. That's because reagents are polar. Nucleophiles are polar, and they are soluble only in polar solvents. So in general, we cannot carry out reactions in non-polar solvents. But polar solvent, as you know, could be protic or aprotic. Protic solvent is hydrogen bond donor, aprotic is not. For that reason, a protic solvent usually retards reaction rate, slows down the reaction rate, because protic solvent forms effective hydrogen bonds with nucleophile, or if nucleophile is not capable of hydrogen bonding, it may form ion-dipole interactions or very strong dipole-dipole interactions. Either way, free electron pairs of a nucleophile are used up in intermolecular interactions and are not available for donation to the substrate. They're not available for reaction. And for that reason, every nucleophile in protic solvents behaves as a weak nucleophile. And so we say that protic solvents exhibit leveling effects. They make every nucleophile a weak nucleophile. But keep in mind that this is correct only in dilute solutions, because in dilute solutions there are enough solvent molecules to form intermolecular interactions with all of the free electrons of the nucleophile. Those are not common reaction conditions. Much more commonly, we carry out reaction in more concentrated solution. And in fact, corresponding protic solvent is the best solvent for alkoxides and of course for hydroxide. So for hydroxide, sodium hydroxide, lithium hydroxide, potassium hydroxide, the best solvent is water. For alkoxides, best solvent is corresponding alcohol. So for sodium methoxide, best solvent is methanol. For sodium methoxide, ethanol, and so on. But reactions are then carried out in concentrated solution. Then we don't have enough molecules of solvent to make hydrogen bonds with all of the molecules, all of the free electrons of a nucleophile. And then a leveling effect is not present. So consider reaction conditions. So to assume that solvent exhibits leveling effect and that every nucleophile is a weak nucleophile, it should be stated that solution is a dilute solution. If that's not stated, then we assume that ordinary reaction conditions are applied, and this concentrated solution, and then this solvent effect actually does not operate. In aprotic solvents, nucleophiles are generally stronger nucleophiles because in aprotic solvents, those that are only hydrogen bond acceptors, nucleophiles are not very well solvated because usually positive end of aprotic solvents, something like carbon or sulfur, and they don't interact very well with nucleophile. So in aprotic solvents, reactions are generally much faster compared to protic solvents. Examples of aprotic solvents are acetone, dimethyl sulfoxide, known by abbreviation DMSO, and N-dimethylformamide, or DMF. And this completes our examination of effects on the reaction rate of SN2 reactions. And next, we'll be looking at SN1 reactions.